Alright, so in this video we're going to explore one special case of implicit differentiation, or if you like, you can really just think of this as a special case of the chain rule, but it's one that frequently comes in handy. So this is called logarithmic differentiation, and the way logarithmic differentiation works is there are certain situations where it's much easier to take the derivative of the log of some function than it is to take the derivative of the original function. And the reason for that is simply that the properties of logarithms often allow us to break down a function. Okay? So first of all, let's see kind of how things work. How do you take the derivative of the log of some function? Well, so if we say y is equal to g of u here, so y is equal to the natural log of u, where u is equal to f of x, then our chain rule says that dy dx is going to be dy du times du dx. So dy du is just the derivative of the natural log function. So we know that's 1 over u. And what's du dx? Du dx is just the derivative of f of x. So f prime of x. And what was u? U was f of x. So we get 1 over f of x times f prime of x, right? Or if you like, simply f prime over f, okay? So whenever you take the derivative of the log of some function, you get the derivative of that function divided by the function itself. Okay, and we'll see how to make use of this. Now, we sometimes have to be a bit careful with things because we do, of course, if we want to be, make sure everything works exactly, the logarithm is only defined for positive values, so really we should only be plugging in functions that are positive here. But we'll find that even in cases where we're dealing with functions that could be negative, this gives us sort of an algebraic trick that gets us to the answer in the end as long as we're careful. Okay, so remember this rule here, right? So the derivative of the log of a function is given by f prime over f. All right, so let's see how to put that to use. Well, here's kind of a scary looking function, right? I mean, it's not bad, but think about how you would take the derivative of this using rules that we know. Well, you've got a quotient, so you'd have to use the quotient rule, right? But then also each part of the quotient here and here, you can see that both the numerator and the denominator are products. So you'd have to do quotient rule followed by the product rule, and then in each we see that two of the terms in each of those products we need chain rule to take care of those, right? I need chain rule here because I have a function raised to a power. Here I have something inside the exponential function. So that's really messy, okay? But I know that since the derivative of the natural log of f of x equals f prime of x over f of x, I can calculate f prime of x is going to be, well, I just multiply both sides, right? It's going to be f of x times the derivative of what goes in here. Well, what goes in here is the log of the function, right? So I take the derivative of the log and then I can solve for f prime. So let's see what the log looks like in this case. So the natural log of f of x, okay, so I get the log of x cubed e to the 5x over x squared plus 1 to the 4 times root x. And so the quotient property for logarithms says that's the same thing as log of x cubed e to the 5x minus the log of the bottom. Let me put that just below so we have room. x squared plus 1 to the 4 times, now that root x, remember root x is x to the 1/2. Okay, so now I can simplify a bit further. I can take the product, right? So I have the natural log of x cubed plus the natural log of e to the 5x minus the natural log of x squared plus 1 to the 4th minus, that minus sign carries through, right? Be careful, that minus sign hits both of these. Minus the natural log of x to the 1/2. Okay, but now remember that powers come down, right? I can bring all these powers down in front. Okay, so let's do that. Let's bring the powers down in front. What do I get then? I get 3 log x. I get, what do I get here? I get 5x. Let's make a bit of room there. 5x times log of e. And what's the log of e? The log of e is just 1, right? So this whole part goes away. I'm just left with 5x. That 4 comes down in front there. My 1/2 goes down there. And if I wanted to, I could take the 3 minus 1/2. I could combine those. I mean, we could have done that at the beginning, I suppose, if we really wanted to. So now I know that the derivative of the natural log of f of x is going to be, so why don't I do that? So 3 minus 1/2, that's 2.5, that's 5 over 2. Okay, so I'm going to get 5 over 2 times the derivative of log x, which is 1 over x. Here I just take the derivative of 5x, which is simply 5. 4 times, well here I take, right, 1 over my function, and then I have to multiply by the derivative of x squared plus 1, which is 2x, right? That's a pretty straightforward derivative to take. So what is f prime of x? Well, I've got to take my original function and multiply by this derivative. So f prime of x is going to be x cubed e to the 5x over x squared plus 1 to the 4 root x times 5 over 2x plus 5 minus 8x over x squared plus 1. And you're done. So that's one reason why you might want to use logarithmic differentiation is that a derivative that would otherwise be quite challenging becomes straightforward. But there are other situations where you've got no choice. Okay, so let's look at this function here. Okay, so I have f of x equals 1 plus x to the 1 over x. Okay, so the natural log of f of x is the natural log of 1 plus x to the 1 over x. But now remember that exponents can come out front. That's one of my log properties. So I get 1 over x times the natural log of 1 plus x. Okay, now I want you to realize that calculating f prime, I have no derivative rule that would let me calculate that derivative as written, right? Both the base and the exponent are functions of x, so I can't treat it as an exponential function. I can't treat it as a power. I need to do something else. So what I can do is this. I take the log of both sides, and now I take the derivative. Because if I take the derivative of both sides, I know that on this side, I get f prime of x over f of x. That's what I get when I take the derivative of the left. And when I take the derivative of the right, well, I can just think of that as a product. Right? So the derivative of 1 over x is minus 1 over x squared. Right? Remember that this is x to the minus 1 times log of of 1 plus x. And then I do 1 over x times the derivative of the log of 1 plus x, which is 1 over 1 plus x. And now I can solve for f prime of x. It's equal to f of x, which is 1 plus x to the 1 over x, times, so 1 over x times x plus 1 minus log of 1 plus x over x squared, and I have my derivative. If I wanted the equation of the tangent line at this point here, right, so x equals 1, y equals 2, I calculate f prime at 1. Okay, I get, so 1 plus 1 is 2 to the power of 1 is just 2 times, so this is going to be 1/2 minus the natural log of 2. All right, so 1 minus 2 log 2. The slope has a natural log in it. That might be a bit of a surprise. So what's the equation of my tangent line? Y minus 2 equals this slope, 1 minus 2 log 2. Or you know what? What's 2 times log 2? That's log of 2 squared. Log of 4 times x minus 1. So there I used log properties to bring that 2 up as a power. Okay, so there's a couple of examples using logarithmic differentiation, and of course we'll do more of these in class.